Hello from New York City. All right, so today's topic is super cool. It is hashing. The idea here is we are going to do a new crazy thing that will allow us to make a set implementation that you might have never thought of. Just a really very cool idea about how to store data. And you can use, once we understand what hashing is and the idea of a hash table, you'll also be able to use it to implement other things like, say, a map, or aka a dictionary. And in fact, Python's dictionary is based on this idea. Okay, so what is this idea all about? Well, let's start just by talking a little bit about how one might build a set. And we've done this before, but hey, do it again. So let's suppose I have an unordered linked list, and it is the engine that drives my set. I have an insert method and a contains method. So when I call insert, I scan through the list and make sure that I don't see anything. Like, say I'm inserting A, I scan through the list to make sure there's not already an A, and if not, then I'll stick it, I don't know, at the front maybe. And then we also have contains, where, okay, does the set contain something? We scan through it and return true if yes. So in this case, if we want to use a linked list, in this case unordered, it will take, in the worst case, in time to do a single contains or insert. And I guess just a very subtle point, this is in, not one, because of the fact that we never want to allow duplicates. Okay, that's one way to do a set, obviously not a very good one. Now, here is an alternate idea. We can instead store our data in a bushy binary search tree, and we support contains and insert operations. And in this case, what would contains and insert take? Well, as you might imagine, suppose we want to know, is J in the set? Doot, doot, doot. Okay, well, I only have to go down one search path, so it should just be log n, and likewise, insert will be log n. So that makes for actually a very good set. And that would be the end of the story, except for two things. One, well, every item here has to be comparable, okay? Now, it's a little subtle point. You don't actually need items to be comparable in order to put them in a set. All you need to do is have equality, right? So for a BST, I have to be able to say K is less than V, okay? But in general with a set, that's not necessary. You don't have to have a total order for all your items. You just have to say they're equal or not, okay? So this restricts the type of data we can even store in a BST-based set. And it's an important one sometimes. And another limitation is that, well, maintaining a bushy tree, when you do insert, if I keep inserting a bunch of really small items that are increasingly small, then my tree will get very unbushy. And we'll be talking about that in the future, but for now, I'll just say maintaining bushiness is non-trivial. So we're going to talk about a data structure today that's going to get around these two limitations. Now this, as it happens, is not the answer, but it will inspire us to greatness. So this is an unordered array, and as you imagine, this makes for a not so good set, right? So if we want to see if something belongs to the set, we have to potentially look through all the items. So suppose it's not there, we'd have to look at every one of them to make sure. Likewise, insert's pretty bad, right? Well, we can stick it anywhere we want, but there's the problem that we're going to have to deal with resizing. So in the worst case, we're going to have to pay n for a resize. Though, I guess if you're willing to discuss amortized time, I mean, inserts maybe not so bad, but certainly contains is bad. So assuming that we have to resize every time, and we can do better, an ordered array is going to be pretty poor, right? So who cares about this? Well, a linked list, as it happens, I'm going to make a random observations that they're not so bad as long as n is small. Okay, duh, right? Of course. If there's not many things in a linked list, we don't really care. But it will be important later. Another observation I'm going to make is that unordered arrays make for pretty terrible sets. Because you have to scan everything to find stuff, and insert, in the worst case, is going to be expensive. Now, as it happens, ordered arrays also pretty bad. I mean, you can get a faster contains, but then insert gets expensive, because if you insert in the middle, you have to move a bunch of stuff. But I'm going to propose that there's actually a third type of array, something else, something a little different, that's going to get us somewhere cool. So here's the idea. All data is just bits, right? If I have a picture file or an MP3 or this video you're watching right now, it is ultimately just a string of bits. So what we could do is whatever data we're trying to store in the set, we could use it as the array index, right? Because every piece of data, this video is a number. So it could be used as an array index, a very big one, but an index nonetheless. And then, as far as our set, however, when we build it, we're just going to store values of true and false in the array to indicate presence or absence. So for example, here is a set. So we create a data indexed integer set, and we add 0, 5, 10, and 11. And the effect is that originally we have an array of a whole lot of booleans that were all false, but now they are true. All right, so we've set them to be true. So this strange array is going to have some really good properties. Intuitively, we expect that this might be quite fast. When we want to put something, we're just setting some value to true somewhere, and whenever we want to check contains, we're just checking a boolean to see if it's true or false. And we'll do an implementation soon to really make sure that's true. Now, there are some significant downsides that I want to first raise before we implement. One of them is that in order to track, so in this case, you'll notice a whole lot of this information isn't really useful exactly. I mean, by default, things are false, and here I'm throwing in all these trues. Ultimately, the problem is we're going to waste a tremendous amount of memory. So here I'm only showing 16, right? But if I wanted to support the ability to put and get any integer, I would need 4 billion booleans, one for each possible integer, because Java, the range is 2 to the 32nd, which is around 4 billion. So we need to somehow keep track of 4 billion booleans. So, okay, yeah, the memory usage is not going to grow with the number of items you put in the set. You're just going to use the maximum possible memory. That's pretty bad. Okay. So if this approach is going to be any good, we're going to have to eventually fix that. And another problem is that, well, obviously, if I'm trying to put the number 5 into this set, I know exactly where to go, index 5. But let's suppose I started putting things like strings or more complicated objects like, let's say, db61b.main objects or something. How do you take that and turn arbitrary objects into a suitable index? Okay, so before we tackle these questions, let's look at what an implementation might look like of this set, this type of set. All right, so let's get cranking on this guy. Data indexed integer set. It is going to have insert and contains methods. So public void insert int x and public boolean contains int x. All right. And I guess we should have a constructor as well, data indexed integer set. Okay, so when we insert something, we know that we just need to set some Boolean array. So it might look something like, let's say, exists. I don't know what I want to call it. Yeah, how about exists? So I'll say exists equals true. And when we want to return, we'll just say return exists x. And of course, when we start up this thing, we'll need to create an array exists. So we'll have Boolean, oh, not Boolean, sorry, exists equals new. Well, let's create the variable for it. So private Boolean exists. And so exists will equal new Boolean. And then I'll just pick some arbitrary large number, let's say. You can make this larger if you want to support larger x's. You can make this extremely large if you're willing to spend all 4 gigabytes of memory in order to store any possible integer. But I'm only going to support up to this, just, hey, because. All right, and at this point, I guess let's do a very rudimentary test. JH class. Okay, so here's all that. That's one of the imports. And we will do some testing just right here in the main. So I create a data indexed integer set equals new data indexed integer set diis dot put 10 15 get, or sorry, contains, I do put insert contains 10, and we'll assume that thing should be true. All right. That should be true, and this should be false. This new thing I picked. Okay. So let's try running it. First try, it worked. All right. The fact that it said nothing is, because we didn't use run junit, that big long command that looks like this. So we didn't use that, so we don't get that nice success message. Just to convince ourselves it really ran, I'll say it really ran. All right, it really ran. Wow, no compile errors and it works. That's how easy it is to write a data indexed integer set. Cool. Okay, so that's data indexed integer set. And I see here I used insert, here I used put. Okay, so who cares really? So the solution for what this code should look like is quite simple. And one of the consequences of this very simple implementation here, as you might imagine, this thing is going to be extremely fast. Because, well, put, all it does is set a single thing in an array, and here this just checks an array. I mean, it doesn't get much better than that, really, right? So if we look at the runtimes, then a data indexed array is going to be constant time for contains and insert. So if we can somehow make this thing actually work, it'll be as fast as a bushy BST, because logarithmic is extremely fast, but we might be able to avoid the mess of needing, 1, comparable items, and 2, somehow maintaining bushiness. So the difference between these two is all about those two problems with bushy BST. So now we're going to have our own set of problems we'll need to sort. What's the word for that? Solve. Wow, somehow store and solve were mixed up in my brain. Anyway, we want to somehow solve this. As an example of the kind of generalization that we're going to have to do to make this something useful, let's talk about how we move from integers to strings. All right. As you notice, I've moved, by the way, and look who's here. Hey, psst. It's Isabel. She doesn't care. You're on the internet, dog. Anyway, I mean, come on. Oh, now she's excited. Okay, anyway, sorry. So suppose we want to store lowercase words instead of storing integers. So what we can do is take each word and turn it into some unique integer representation. So what I'm proposing here for the word cat is let's take each letter and use it as a 5-digit binary number and just stick all the binary numbers together to form one giganto number that we can use as an index. So for example, since the letter C is the third letter of the alphabet, we'll replace any instance of C in some sense. I mean, we're not really replacing anything, but we'll represent C by 0011, which is 3. A by 1, T here by 10100, since this is the 20th letter of the alphabet. Okay, so why 5 bits? Well, because the alphabet has 26 letters in it, so that's the minimum number of bits we need to capture these letters. So now what happens is when we want to put a word like, say, cat or dog or potato, we will calculate a big integer like this, in effect treating it like a up to 6-digit base 32 number. So T plus A times 32 plus C times 32 times 32, and so forth. Okay, and so what happens in this case is we end up with, again, a giant Boolean array. And here when we've added these 4 strings, we will have set the indices 3,124, 4,583, and so forth to true. And then we're left with a few tens of millions of false Booleans that seem a little silly. Okay, so this is one approach, and it'll work perfectly well, of course, until we start looking at really long words. So a funny thing happens when you get up to really long strings. We end up with a situation where our strings no longer fit inside of a 32-bit number. So why not use bigger array indices? Well, one, obviously that's going to cost us. Every bit we add is going to double the memory we require, but also just more fundamentally, Java, if we're using arrays, does not allow, say, long integer array indices. You get 32 bits, that's it. So what that means is that if we want to somehow be able to handle longer strings, well, one thing we could do is say we're not going to handle longer strings. Sorry, we'll only take 6 letters, but we can alternately just allow some kind of ambiguity somehow. So let me give you an example of ambiguity. So if we have the words hothead and pothead, which honestly are a little opposite, we find they have the exact same representation here, right? So hothead, pothead, hothead, all of those are going to be represented by exactly this. So if we have a true here, we don't know if that's hothead, pothead, or what. All right. That could be problematic, depending on what you're using your set for. Okay. So we're going to say that we want to somehow fix this approach. We want to make it better so that we can resolve this ambiguity. Because it's not acceptable for us to just say, well, sorry, my data structure doesn't let me tell. You put in hothead, and I will say, in fact, there's a pothead here. That's not allowed. So we're going to have to do something clever to make this work, but at least this lets us appreciate the trouble we will reach. So before we get to resolving that, let's look at an implementation of this data structure. Okay, so here's data indexed word set. And we'll just delete this comment because this isn't real code, so hey, bye comments. Data indexed word set. Okay, so in this case, we now want to do public void. What are we using? Put. All right, I'm gonna switch back to put to match what the slides usually say. So public void put string s. We want public int, public boolean contains string s, and that's that. Okay, and I guess, well, we'll add a constructor. Okay, so if we have a constructor here, we'll again use exists, and I'll pick again some arbitrary large number. New boolean 1. All right, that should do for now. Maybe we'll make it slightly bigger. Okay, so when we want to check contains, we need to first convert the string into actually, we'll do put first. So what we want to do is have, let's call it int rep for integer representation. So the integer representation will say, we'll have convert to int s, right? At that point, we will just write put, well, no, we can't call put. That would be recursive. Then we'll just do exists int rep equals true, and that's it. All right. For contains, we'll do something very similar, and then we'll say return exists int rep. Okay, so now all that remains to be done is to write this convert to integer function. So we'll notice it's very similar to an integer set. The only difference is that now we have to make an integer representation. So I guess we'll make it private. The world doesn't have to know about our secrets. And in this case, we'll convert it to an int. So how might we do that? Well, there is a handy function that strings support called char@, where we can say, for example, for int I equals 0, I is less than s.length, I plus plus, or, well, we'll pol out and make this pol plus equals 1. And we need, let's say, int rep, start it off at 0. And then we'll just take the last, or the ith character. Let's see, yeah. We'll take the ith character, and we'll convert it to a number between 1 and 26. All right, so we need to, let's say, convert to, what would we call that? Letter number. All right. So convert to letter number, and here we do, okay, private int convert to letter number. In this case, we get, so this thing returns a character. So we'll have character C. So to convert to our letter number, we'll just return C minus A plus 1. So in other words, if we provide it with quotes A, recall from our number representations lecture, this is just some integer. So we take whatever letter you gave me, subtract away A, and add 1. So A should end up being 1, B should end up being 2, and so forth. So int rep doesn't equal that, it's plus equals that. So we add the most recent digit, although that's not all, right? We actually need to, whatever digits we put in first, whatever letters we put in first, we will have to shift them up by 5 bits. So int rep equals int rep shifted by 5. Int rep plus equals whatever current letter, and then we'll return int rep. Okay. So this will provide us with an integer representation of our string where each character is converted into first a 5-bit number, and then each digit is shifted to the appropriate location so that we end up with one big whole integer. And of course, if it gets too big, well, too bad. Then the letters that came in first are thrown away. Okay. So here we go. So we have convert to int, contains, put, and now let's try it out. So I want to make a data indexed word set. New data indexed word set. And now I should be able to put things like hello, cat, so forth. I will be able to say assert true that this contains cat. I should also be able to say that it contains hello, obviously. We'll do assert false, that something we didn't put in is gone. And then let's try out our gross pi. Actually, let's just try running it and fix whatever is broken now. Okay, so we have a bug, array index out of bounds. Okay, so oops, we did not pick a big enough number. All right, we'll add another 0. Cross our fingers that it works. Okay, it worked. And again, since I'm not using run JUnit, we don't get the glorious success, but I'll put success here. Okay. Yay, all right, it worked. So now let's explore that collision issue, as we'll call it soon, where we have two words that have the same index. So one way in which we might see some ambiguity is, for example, in the words, if we add Iceland, and we try and compare that to, let's say, Miceland. All right, two very different places. And I'm going to throw in a little print statement here so we can actually see all of the integer representations as things get put in. So when I run this code now, I see, too big. All right, going to make our array larger. But we can see the hello, cat, and here, Iceland. So actually, let's add some more. Okay, that should do. Computer, do you have, all right, well. So now it works. And what we'll observe is that Iceland here and Miceland here have the same exact index. So if I take away that put call, and I instead just say, hey, I believe it should be false that diws contains Miceland, we run this and see, ooh, in fact, contains Iceland. Not sure what that was. Okay, so we try running this, and we find that, failure. In fact, our array contains Miceland. It's probably a very cute place, but not a place we intended to go.
So what are the key points with this implementation? We note that whenever we created our data indexed word set, that contains and put looked pretty much the same as before, except that we had this intermediate step where we had to convert our strings to integers, right? That's it. We have this extra little layer, and we end up with pretty much the same data structure. Now, of course, converting to int is not a trivial process. We had to write a bunch of code. Here's a slightly more industrial strength version, even with a comment. Ooh, that will convert a string to an integer. Okay. Well, the big picture here is there seems to be a generalizing principle. If we can take a piece of data and turn it into an integer, then maybe we can get a good data structure out of this. But we're still left with a couple of major challenges. One is, how do we resolve ambiguity? So if someone gives us the string gross pi versus boss pi, I mean, I certainly want to know which kind of pie I'm going to get before I eat it. And another one is there some good way? What do we need to do? What makes for a good conversion function? The one we had so far seems to lend itself to ambiguity pretty easily. So is there something we can do better? And I'll mention that, by the way, this principle we're using, this is not just some silly thing that I'm just making up as we go. In fact, this idea of taking data, any object, and turning it into an integer is so fundamental that is one of the few things that all objects must do. That is hash code. Hash code is this number right here. And so we'll talk about this at the very end of this lecture as to what makes a good hash code. But ultimately, if we want to make this data indexed array into a real usable thing, we're going to have to solve these two challenges.